Hello everyone, my name is Elias Munthali and I'd like to welcome you to my presentation entitled Intensity of Wastewater Treatment Upstream Reservoir Defines the Resistance of its Water Quality to Extreme Climatic Events. This is part of my PhD work, which is jointly supervised by Rafael Marseille from Catalan Institute for Water Research and Lisette Senenpont-Delmis from the Netherlands Institute of Ecology. As can be seen from the title, this work is centered on eutrophication and extreme climatic events. So let's begin by defining these two terms. Eutrophication is defined as over-enrichment of aquatic ecosystems with nutrients leading to algal blooms and anoxia. The United Nations Environmental Protection Agency reports that currently over 40% of the world's water bodies are experiencing moderate to severe eutrophication. And due to climate change, eutrophication is projected to worsen. From a drinking water perspective, eutrophication is associated with increased organic matter production, formation of anoxia, and the release of iron and manganese from sediment base into the water column. All of these are associated with increased treatment cost or treatment failure. Extreme climatic events are ecologically defined as events where unusual values of climate variables result in rare responses of ecosystems. For example, heat waves, drought, and storm conditions. And the Intergovernmental Panel on Climate Change reports that due to climate change, these extreme climatic events are projected to increase in intensity, magnitude, occurrence, and variability. The impact of these extreme climatic events on lake is varied. For example, studies elsewhere have shown that heat waves are associated with increased eutrophication, yet somewhere else, some people have shown that the same heat waves are associated with a reduced nutrient concentrations in surface water layers. Droughts have been shown to show eutrophication and algal blooms. Extreme rainfall has been associated with increased turbidity and causing cyanobacteria blooms in lakes, yet some studies have shown that the same extreme rainfall events are associated with a reduced eutrophication due to flushing out of lakes. What has not been studied before is whether a change in trophic state of lakes from being eutrophic to mesotrophic or oligotrophic increases the resistance of its water quality to impacts of extreme climatic events. This then brings us to the main objective of this study, which is basically to explore the dynamics and the resistance of soil reservoir water quality to impacts of extreme climatic events in two distinct periods separated by a trophic state change in lake following the upgrades of wastewater treatment plants in the TANTE catchment. Our study is based on a data set spanning over a period of 55 years collected on soil reservoir, which is situated on the middle stretch of the Tail River. This dataset comprises of depth profiles of water temperature, dissolved oxygen, nitrate, ammonia, and total phosphorus. It also has data on stream flow, water level, precipitation, and maximum air temperature. In our study, we are combining this dataset to carry out a series of analyses amounting to about 5 of them. In the first analysis, we take monthly accumulations of precipitation and monthly accumulations of inflow and monthly averages of water level and feed them into a computational framework which is based on the Gringo 10 plotting position. What this framework does is that from each time series, it takes up the zeros and ranks the remaining figures in the order of increase in size. And then it computes the empirical probability with which it applies the standard normal distribution function to convert it into standardized indices. The outputs are the non-parametric standardized precipitation index and the non-parametric standardized stream flow index, as well as the non-parametric standardized reservoir level index. So the computational framework for Heatwave works as follows. It takes in the daily maximum air temperature values and then defines the reference period as the values between 1981 to 2011. So that's a period of 30 years. And then it calculates the heat wave for a particular day by taking the temperature for that day and subtracting the 25th percentile from that temperature value, and then divides the result by the interquartile range which is the difference between the 75th percentile of the reference period and the 25th percentile of the same reference period. The output is the unitless figure, which represents the maximum heat wave for that particular year. The third analysis aimed at aggregating daily depth profiles of water quality into the epilemion and hypolemnion time series. To achieve that, daily depth profiles of water temperature were fed into the lake analyzer tool together with the reservoir bathymetry data to generate the top and bottom metalemnion depth. The generated metalemnion depth were then coupled to water quality depth profiles to delineate which depth profiles belonged to the epilemion zone and which ones belong to the hypolemnion zone. For the ones that belong to the epilemion or hypolemnion, they were then averaged to give one single value for water quality for that day. And then the entire time series was built following that approach. The fourth analysis aimed at establishing causal relationships between hydrometeorological variables as predictors and epilimnetic and hypolimnetic water quality time series as response variables. To achieve that, we adopted the non-parametric causality-in-quantile methodology, which is mostly applied in economics research. This method is an extension of the Granger causality framework, in which if you have two time series, yt as a response variable, in our case that's the epilimnetic and hypolimnetic water quality time series, and xt as a predictor variable, in our case the hydrometeorological variables, then xt is assumed to Granger cause yt if the model that includes both the lagged values of the response variable and the predictor variable performs better in comparison to a model that includes only the lagged values of the response variable. This method is only meant to address the linear relationship in means. So, because the relationships might not be linear at all times, other researchers extended the methodology to include causality in quantiles as well as to address nonlinear relationships. The output of this methodology is the distance measure test statistic, which is compared to the confidence level at which you conducted the hypothesis testing. In our case, we did the analysis at 95% confidence level, and our critical value is 1.96. The interpretation of the result is that causality is assumed to have occurred if the computed test statistic is above 1.96. Otherwise, if it is below, then there's no evidence of causality. This J statistics is basically a comparison of those two models which I mentioned earlier on. In the fifth analysis, we sought to understand the impact of extreme events on water quality. So let's begin by looking at how we approach the analysis of extreme drought or wet conditions on water quality. First, we picked the time series for drought or wet conditions and clustered them using the peak over threshold approach. And then we picked the maximum values from each cluster and coupled them to epilimnetic and hypolimnetic water quality series. And so doing, we removed autocorrelation from both the extreme events time series as well as the water quality time series. Next, the coupled time series were split into the before period, which represents the time before wastewater treatment facilities were built in the catchment, and the after period, which is the time after wastewater treatment facilities were built in the catchment. After the split between those two periods, the time series were further split into the extreme drought and non-extreme drought conditions, or extreme wet and non-extreme wet conditions, through application of thresholds. For example, extreme drought conditions were all those conditions in which the value of the indices were less than 1.3. And the non-extreme cases were those in which the value of the indices were greater than 1.3 but less than 0. Similarly, extreme wet conditions were defined as those conditions in which the value of the indices were greater than 1.3, and the non-extreme cases were all those in which the value of the indices were greater than 0 but less than 1.3. Following that split between the extreme and non-extreme conditions, then the impact of extreme events were analyzed by comparing the means of water quality falling in the categories of extreme and non-extreme through the use of the wedge test. The output of that analysis were the bias factor values, which were ranked according to thresholds. The analysis of the impact of heat waves was slightly different because heat waves only occur in summer. We approached it in the following ways. First of all summers with heat wave magnitude index greater than 0 were selected, followed by picking the maximum heat wave for each summer which had a heat wave. Then they picked maximum heat wave magnitude index daily values were coupled to the epiliminetic and hypoliminetic water quality time series. And then they were split into the before and the after periods as in the previous slide. Then the August mean water quality values for all summers with the maximum heat wave magnitude index daily were compared to all summers in which the value of the index were 0 using the wedge test to yield the bias factor values, which were then categorized by using the thresholds of evidence. Let's now delve into the results section, and we begin by looking at results from the Causality-in-quantile analysis. The output of that analysis is a plot of the test statistic J on the y-axis versus the quantiles on the x-axis. There are 3 lines in each plot. There's a green line, which is a threshold at which the hypothesis was tested. In our case, it was 95% confidence level, giving us a value of 1.96. There's a blue line, which represents test statistical results from the hypolimnion, and the brown line represents test statistical results from the epilimnion. A particular predictor is adjudged to have causal influence on response variable if the plot of the J statistic is above the threshold level. Otherwise, if it is below, it means there's no evidence of causality. In our case, we have 4 panels, which represent 4 predictors that were used in our analysis. So we have a panel on the top left, which represents results for air temperature as a predictor. We have a panel on the bottom left, which represents precipitation as a predictor. We have a panel on the top right, which represents inflow as a predictor. And finally, we have a panel on the bottom right, which represents results of water level as a predictor. The summary of the hypolimnion results are as follows. We see stronger evidence of causality in the before period compared to the after period, especially in dissolved oxygen and in nitrate. And in those results, we see a stronger evidence of causality in the lower quantiles of the response variable, meaning evidence of causality tails off as the levels of quantiles increase in the response variable. There's an exception that we note in ammonia, because evidence is weaker in the before period and it gets stronger in the after period. When we look at the epilimnion, the results show that causality in the epilimnion was less strong compared to the hypolimnion, and in some cases it was totally absent. So for example, if you look at the brown line in all the 4 panels, they are pretty close or they are below the threshold level. Again, we note the exception in ammonia, which shows that evidence of causality was stronger in the after period. So if we look at the brown line in all the 4 panels, for ammonia, it looks like it was a little bit higher, especially for air temperature, for inflow, and for water level. The second set of results that we want to present are the extreme event impact on water quality. We are presenting those results in form of 2 tables. So we begin by looking at the hypolimnion. So each of those 2 tables contains a column with information on the type of extreme event itself. The second column has information on the hydrometeorological time series from which the extreme event was derived. Then columns number 3 to number 7 contain 2 types of information. The first information is the coloring corresponding to the bias factor evidence level. These bias factors were computed as a statistical comparison of mean values of water quality between events classified as extreme and events classified as non-extreme. Then the second set of information are the actual figures that you see in the grids. Those figures relate to the numerical difference between mean values of water quality for events classified as extreme and events classified as non-extreme. So the summary looks like this. For example, we see that in the hypolemon, heat waves decreased the mean value of dissolved oxygen in the before period, but the same heat waves did not do anything on dissolved oxygen in the after period. Instead, it decreased the mean values of total phosphorus. When we look at drought conditions, we see that extreme drought conditions decrease the mean values of dissolved oxygen, increased the mean values of ammonia, and increased the mean values of temperature. In the after period, the same drought conditions did not result in any change of the mean values of water quality. When we look at extreme wet events, we see that they increased the mean value of dissolved oxygen and nitrate, but decreased the mean value of ammonia and total phosphorus. The same events increase the mean value of temperature. And in the after periods, it's only dissolved oxygen which looks to have responded to the extreme wet events. The other water quality variables do not respond to that. When we look at the epilemium, the type of information is the same, and the summary is like this. We see that heat waves did not have any impact on any water quality variable in the before period, but it did decrease the mean value of nitrate in the after period. The drought conditions, we see that they decreased the mean value of dissolved oxygen and nitrate, but increased the mean value of ammonia and temperature in the before period. In the after period, the drought conditions increase the mean value of ammonia and decrease the mean value of temperature. When we look at wet conditions, we see that in the before period, they did increase the mean value of nitrate and decrease the mean value of ammonia. Yet in the after period, the same extreme wet conditions only increased the mean value of dissolved oxygen, reduced the mean value of ammonia, and reduced the mean value of total phosphorus. In essence, what we see is that while there is a pattern that extreme climatic events affected water quality more in the before period in the hypolemon, and almost didn't affect any water quality variable in the after period, we see that the outlook in the epilemion is a little bit of a mixed bag. Let's conclude this presentation by pointing out a few things that we observed from the analysis. First, that water quality became more resistant to extreme climatic events in the after period was confirmed by both the Causality-in-quantile and the extreme climatic event impact analysis. Both analyses also showed that change in resistance to extreme climatic events was stronger in the hypolemon compared to the epilemion. We think that the observed differences in the resistance of water quality to extreme climatic events between the epilemion and the hypolemon are governed by two different metabolic processes. One, organic matter synthesis anabolism, which happens in the epilemion, and two, degradation of organic matter, which is called catabolism, and which we think happens in the hypolemon. Hypolemon water quality was more predictable because organic matter degradation in deeper layers doesn't show short-term oscillations that are typical of organic matter synthesis. Hence, our methodology was able to capture the dynamics using the MANTEL resolution of our data set. Insensitivity of dissolved oxygen to extreme climatic events in the after period was related to increase in dissolved oxygen following decreased organic matter loads, hence low dissolved oxygen consumption. we think we are contributing a novel approach suitable for tracking footprints of extreme climatic events in low frequency datasets. The current approach is that we only think that we can capture the dynamics of extreme climatic events in lakes by using high frequency data. Yet, we have just shown that it's possible to find the footprints of the impacts of climatic events by using the monthly resolution dataset that we have. We also think we're adding a novel approach for analyzing climate effects on lake water quality on top of the traditionally used methods of correlations, linear regression analysis, and mean comparisons. Having looked at everything, what is our take-home message from this analysis? We think that our results suggest that keeping lakes in good trophic state makes water quality more resistant to impacts of extreme climatic events. At this point, I would like to thank you for watching. Have a good day.